Hello everyone. In this video we are going to cover, or at least start, section 8.2 on series, where we introduce the notion of an infinite series. So in the last section, 8.1, we introduced the notion of a sequence, which is literally just a list of numbers, right? So an infinite sequence is just an infinite list of numbers. And so what we're going to do with this infinite list of numbers is just start adding them up one by one. So the way we denote that is with this symbol here, and the n equals 1 at the bottom tells you to start with n equals 1 if that's where you begin, and you don't stop, right? You just keep going until infinity. For short, you may also see this notation when it's clear where the sequence starts and ends. So it may help to think of this, it's a sigma, which means sum. This is the Greek letter, what they use for S, what we call S. But think of it as like a big plus sign, right? So what it's telling you to do is start with n equals 1, so you get a1, so plug in n equals 1, and then big plus, plug in the next integer, so n equals 2, right? Plus, plug in the next integer, a3, right? N equals 3, so you get a3. Plus, and so what this is telling you is just keep adding every single time you plug in a new integer. Okay. So there was actually a typo here. It's actually not acute chili, but I should say that I've re-uploaded the Chapter 8 notes, hopefully catching some more typos. If I'll try to make note of them if I remember. But you should probably download the new Chapter 8 notes just to catch any typos. Okay, so here's the miraculous part. So read this remark. It says that it's actually possible, even though you're going to be adding up infinitely many terms, it's possible to still get a finite answer. And so I guess a good example of this is, let's look at the sequence 3 1/10, 4 100ths, 1 1,000th, 5 10,000ths, etc., etc. So if I take the sum of this sequence, right, and this is called a series, right? Well, once you put the sigma there, it's called a series. Then let's see what we get, right? So you get 3 plus the next one, plus the next one, plus the next one, and so on and so forth. And this goes on indefinitely, right? And so let's look at what we get. Well, we get 3 plus, let's see, 1/10 is 0.1. Now 4 over 10 squared is 0.04. Plus, now this is 1 over 10 cubed is 0.001. Plus 0.0005 plus 0.00009 plus 0.000002, and so on. And what you'll notice is that what this sequence actually does, when you add it all up, you get a series where you just fill in the next decimal value. Notice here I get a 3, then in my 10th position I get a 1, and nothing else contributes to the 10th position, because notice they're all zeros thereafter. In the 100th position I get a 4, in the thousandths I get a 1, then I get a 5, 9, 2. I bet you know what the next one is, probably 6. This is just pi, right? So, which is a finite number, right? So this is kind of a cheeky example to show you that you can add up infinitely many things but still obtain a finite answer. And I mean, really what's going on here is that, like, you'll notice eventually you would hope that the decimal values don't stack up on each other. They didn't stack up at all, right? So 3, nothing else contributed to the 1's position. Once I got the 0.1, nothing else contributed to the 10th's position, and so on and so forth. So that's how it actually happens that you'll get a finite answer, is if the decimal values don't stack up on each other. Okay, now let's look at this sequence here. This is called a geometric sequence. And so when I take the sum n equals 1 to infinity, when I form the series 1 over 2 to the n, this is called a geometric series, right? Because it's formed from a geometric sequence. Well, this is 1/2 plus 1 over 2 squared. And I'm going to write it like this, just so, because I don't feel like writing, 1 over 16 and that kind of thing. Okay, so let's see what happens. Let's come over here to a number line. You'll notice when I plug in my first value, I get 1/2, right? So that's right about here. And then when I do my second sum, I get 1/2 plus 1/4. Well, 1/4 more than 1/2 is about right here. That's 3/4 technically, but I'm going to leave it as 1/2 plus 1/2 squared. Hopefully you'll see a pattern. Now, when I tack on the third thing, right? So this is 1/2 plus 1/2 squared plus 1/2 cubed. And now maybe you can see what's going to happen when I tack on the fourth thing, the 1/2 to the fourth. That's going to get me halfway more towards 1 from where I previously was. So that's 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. And now I'm running out of room, but I think you can see when I add on that fifth one, this is going to be 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth plus 1/2 to the fifth. And then when I add on the 1/2 to the sixth, I'm here and here, and now I'm running out of room, but we have a dot, 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 and it looks like I'm going to be sort of limiting towards 1, right? And in fact, that's exactly what this infinite series, what the value is. So this infinite series, when I add up 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, I get exactly 1. You know, I have to keep adding indefinitely, but and we're actually going to be able to verify that soon enough, but that's kind of a neat fact. Okay, so just another example for you of infinitely many things adding up to a finite number. And in fact, 1 is a very nice finite number. But you see this notion where we took the first value, sort of plotted it, then we looked at added up the first 2, plotted that, added up the first 3, plotted that, added up the first 4, etc. That's going to be an important principle that we'll get to in just a minute. But let's see, sometimes you can add up infinitely many things and obviously not get a finite answer. So if we look here, if we take the sum n equals 1 to infinity, now you'll notice an is just n itself, right? When n is 1, I get 1. When n is 2, I get 2. When n is 3. So this is just the sum from n equals 1 to infinity of just n. So that's 1 plus 2 plus 3 plus 4 plus etc. Well, I mean, let's look at what's happening here. When I look at just the first one, I get a 1. When I add up the first 2, I get a 3. Add up the first 3, I get 6. Add up the first 4, I get 10. Add up the first 5, I get 15, right? So it's like these, what are known as partial sums, are kind of getting bigger and bigger, right? I think the next one would be 21, etc. Right? And so you'll notice that every time I just add up the first so many and then put them into a new list, I actually get a new sequence. So this sequence, or I'm sorry, this infinite series here diverges. And the reason this infinite series diverges is because when I add up the first one, put it in the first entry here, add up the first 2, put it here, add up the first 3, put it here, add up the first 4, put it here, etc., etc. This list of numbers, i.e. this infinite sequence, you can see pretty clearly diverges, right? So this is actually how we define convergence or divergence of an infinite series. What we do is we consider a new sequence of what are called partial sums. And I refer to this partial sum finding business as using first principles. But let's actually go up above and see how this worked out for us earlier. So you'll notice here I could actually make a new sequence out of these partial sums. So first just plug in 1, I get 1/2. Then if I add up the first 2 things, I get 1/2 plus 1/2 squared. And that was this number here, right? Then add up the first 3 things, and that was this number here. And then add up the first 4 things. I'm not going to write it down, but you see we get a new infinite list of numbers where you always add up the first so many terms of this series. And this new list of numbers, in fact, actually converges to 1. And that's why we say that the infinite sum, this infinite series here, has a value of 1. It's because this list of numbers that I've come up with also converges to 1. All right, so here's how you do it in general. Let's say you have a sequence and you want to find the partial sums. We call that Sn. So Sn is just going to be A1 plus A2 plus all the way up to An. And so that's why S1 is just always equal to the first thing. S2 is equal to the sum of the first 2 entries in the sequence. S3 is the sum of the first 3 entries in the sequence. So I want to make a remark here that a sequence and a series are not the same notion, right? This one, you're adding infinitely many numbers. Whereas this one, a sequence, is just literally an infinite list of numbers. So you see the difference? The difference here is that a sequence is just an infinite list of numbers, whereas a series, you're adding up infinitely many numbers. And then that's what this notation means, right? It means add up the sequence AN. Here, this one is just a list of numbers. You use curly braces to denote that. Whereas here, this is telling you what to do with those numbers. Add them all up, right? But the connection between the two, and that's what this partial sum first principle business, and form a new sequence. A1, A1 plus A2, A1 plus A2 plus A3, and so on. And now, if this new list of numbers converges, we say that that's what the infinite series also converges to. And if it diverges, then we say the infinite series diverges. Okay, so hopefully that's cleared things up. But this is called the sequence of partial sums. Okay, we'll be looking more at that in the next video when we learn how to find the sum of a geometric series.